Myself Shweta. Today we discuss the chapter Physical Properties and Molecular Structure. Introduction. The various methods used for the study to molecular structure may be broadly classified into the following two types. First one is methods based upon the study of physical properties of the substances such as first, molar refraction; second, paracore; third, optical activity; fourth, dipole moment; fifth, magnetic susceptibility. Second one is spectroscopic methods such as first one is rotational and vibrational spectroscopy, second one is electronic spectroscopy, third one is Raman spectroscopy, and fourth one is nuclear magnetic resonance, that is NMR spectroscopy. The study of molecular structure on the basis of physical properties is based upon the fact that the physical properties listed above are additives as well as constitutive. An additive property of a molecule is defined as that property the total value of which is the sum of the values of its constituent atoms. A constitutive property of a molecule is defined as that property which depends upon the constitution of the molecule, that is, arrangement of atoms within the molecule and the presence of multiple bonds, rings, etc. in the molecule. Spectroscopic methods have already been discussed in chapter 3. Now, in this chapter, we shall take up a brief discussion of three important physical properties, namely optical activity, dipole moment, and magnetic susceptibility one by one. There is a topic named as optical activity. Definition 1. Plane polarized light. If a ray of light travels in any direction, it has vibrations in all directions at right angles to the path of propagation. Figure 5.1. If this light is passed through Nicol prism, then the light a Nicol prism devised by the scientist Nicol consists of two prisms joined together as shown in figure 5.1. Each of these prisms is made out of a substance called Leland spar or calcite. If a single prism is used, it is found that two beams of light come out, each of which is plane polarized, and the planes of the two are at right angles to each other. By combining with second prism, one of the beams undergoes total internal reflection and only one plane polarized beam comes out. Instead of Nicol prism, a Polaroid is also sometimes used. It consists of a film of cellulose acetate between two glass plates, which emerges out of the prism is found to have vibrations only in one plane. The light is called plane polarized light. The Nicol prism thus used is as called a polarizer. Second one is optical activity. If the plane polarized light is passed through a plate of quartz or turpentine oil or the solution of sugar, it is found that in the light that comes out, the plane of the polarized light gets rotated. The substance like quartz, sugar, etc., which rotate the plane of polarized light are called optically active substance. And the property of a substance to rotate the plane of the polarized light is called optical activity. The substances which rotate the plane polarized light to the right are called dextrorotatory, and those which rotate the plane of the polarized light to the left are called levorotatory. The method of observing the rotation of the plane of the polarized light is based upon the following principle. If plane polarized light is passed through another Nicol prism which has its axis parallel to the of the first Nicol prism, the light passes through the brightness as observed things the eyepiece On the other hand, if the second nickel prism is placed with its axis at right angles to that of the first prism, the light is completely cut off and field of view in the piece is dark. At all other positions, the brightness is less, but there may not be complete darkness. It is observed that if the two Nicol prisms are set at the crossed position so that the field of view is completely dark, and then the optical active substance is placed between the two prisms, the field of the view becomes somewhat bright. The second prism has to be rotated though certain angle about the line of propagation of light to get complete darkness again. This clearly shows that after passing through the optically active substance, the plane of the polarized light has been rotated. The degree of rotation depends upon the rotation required to be given to the second Nicol prism to get the darkness again. This just at the first prism polarizes the light and it is called polarizer. The second prism analyzes the light and it is called analyzer. Third one is specific rotation. The angle in degrees through which the plane of the polarized light is rotated on passing through the solution of an optically active substance depends upon the following factors. First one is nature of optically active substance. Second, concentration of the solution. Third, length of the tube. Fourth, wavelength of the light used. Fifth, the temperature of the solution. If m grams of the substances are dissolved in v ml of the solution, L is the length of the tube, alpha is the angle of rotation, then it is found that alpha is directly proportional to concentration in gram per ml into length of the cube in decimeter. Alpha is directly proportional to m by v into L, or alpha is equal to alpha alpha close bracket. In the lower side this is lambda and the upper side this is temperature m into L by V, where this is a constant characteristic of the nature of the substance and depends upon the wavelength of light used and the temperature of the solution. If D line of the sodium vapor lamp light used and the temperature of the solution is 25 degrees Celsius, then it is written as alpha and the lower side is D and the upper side is 25 degree. This constant is called specific rotation of the substance. Thus from the above equation, alpha lower side is lambda and the upper side is T is equal to V into alpha by me L into me M. Now if M is equal to 1 gram, V is equal to 1 ml and L is equal to 1 dm, then alpha is equal to normal alpha. Hence specific rotation of a substance may be defined as the angle of rotation produced when 1 gram of the substance is dissolved in 1 ml of the solution. In all reported values of alpha, the concentration of the solution is taken in grams per 100 ml of the solution. Thus, if C grams are dissolved in 100 ml of the solution, then we may put M is equal to C and V is equal to 100. Then the equation goes to equation third, that is constant characteristic is equal to 100 into my alpha by my L into my C for solutions. And for pure liquids or solids, constant characteristic is equal to alpha by my L into my D for pure liquids or solids. Fourth one is molar rotation. The molar rotation is obtained by multiplying the specific rotation with the molecular weight of the substance and dividing the result by 100. It is usually represented as bracket close m and the lower side lambda and the upper side T. Thus, M, which have a lower side wavelength and upper side is temperature, is equal to M into my alpha by my 100. There is another topic, measurement of optically activity, that is the angle of rotation alpha. The instrument used for the measurement of the amount of rotation in degrees caused by an optically active substance to the plane of the polarized light is called polarimeter. The principle of this instrument has been already discussed. It consists essentially of two nickel prisms, one called the polarizer and another one is analyzer. Both of these are fitted on the opposite ends of the same metal tube. However, the polarizer is fixed but the analyzer can be rotated about the axis of the tube. In between the polarizer and the analyzer, there is a space for keeping the glass tube containing the solution. The glass tube is usually 5 cm, 10 cm, 20 cm, and 25 cm and has glass windows on both ends. A circular scale is fixed on the metal tube near the analyzer. In the procedure, first of all, monochromatic light from a suitable source is passed through the instrument without placing the tube containing the liquid or the solution. The light emerging out of the analyzer is viewed through the eyepiece. The analyzer is then rotated slowly till the field of view is completely dark. This gives the initial reading of the instrument. Now the tube containing the liquid or the solution is placed and the shutter closed. On seeing through the eyepiece, the field of view is no longer found to be dark. The analyzer is rotated slowly till the field of view is completely dark again. This gives the final reading. The difference between the final reading and the initial readings gives the angle of rotation alpha. If it comes out to be positive, the substance is dextrorotatory, and if negative, it is levorotatory. There is another topic, optical activity and chemical constitution. Optical activity is a purely constitutive property. It depends upon the arrangement of atoms within the molecule. It has been observed that the organic compounds which are found to be optically active contain at least one carbon atom to which four different atoms or groups are attached. Such a carbon atom is called an asymmetric carbon atom and is usually shown by putting a sign of star over it. A very simple example of such a compound is that of lactic acid. It is found that such a compound exists in two forms, one of which rotates the plane of the polarized light to the right is called dextrorotatory, and the other which rotates the plane of the polarized light to the left is called levorotatory. The two forms have the same constitution, thus the two forms are space isomers called optical isomers. Leibel and Van 't Hoff pointed out the differences in the two forms by suggesting that in case of such molecules, the asymmetric carbon atom is present in the center of a regular tetragon and the four atoms or groups attached to it are present at the corner of the tetrahedron. This gives rise to two different spatial arrangements which were like the mirror images of each other. The above two configurations are different in the sense that they are not superimposable over each other. Thus, the two forms are related to each other as the right hand is to the left hand of the same person. The above two forms may be represented in a simple way as follows. In Form 1, the arrangement from H to OH is clockwise, and in Form 2, the arrangement from H to OH is anticlockwise. Hence, if one them is dextrorotatory and the other is levorotatory. However, by inspection of the configurations, it is not possible to predict as to which form is dextro or levo. The two forms are said to be enantiomorphs. Further, if equimolar quantities of the two forms are mixed together, a third form is obtained which is optically inactive. This is obviously due to the fact that the rotation caused by one form to the right is nullified by the equal rotation caused by the second form to the left. The process is called external compensation, and the substances thus obtained are called racemic mixtures. This form can be separated into D and L forms by suitable methods. In case of compounds containing two asymmetric carbon atoms, a fourth form is also found to exist. In this form, the rotation caused by half of the molecule is compensated by the other half within the molecule, as shown in this figure 5.5 for tartaric acid. This form, which is optically inactive due to internal compensation, is called mesoform. Lastly, it may be mentioned that optical activity is found not only in the organic compounds containing an asymmetric carbon atom but also in the compounds which contain other asymmetric atoms like nitrogen, sulfur, silicon, cobalt, tin, etc. Further, some compounds may not contain an asymmetric atom but are optically active because the molecule as a whole is asymmetric. Thus, it may be concluded that the optical activity is a property related with asymmetry of the molecules. Hence, optical activity can be used to test the presence of asymmetry in the molecule. There is another topic 5.3 dipole moment general introduction. First one is polar and non-polar covalent bonds. A covalent bond is formed by the mutual sharing of electrons between two atoms. If two atoms are identical, example H2Cl2 etc., the shared pair of electrons is attracted equally by both the atoms and hence it remains exactly in the center of the two atoms as shown in below. Thus, neither of the two atoms in such molecules acquires positive or negative charge. The bond thus formed between two identical atoms is called non-polar covalent bond. On the other hand, if the two atoms are dissimilar, example in the HCl molecule, chlorine atom is more electronegative than the H atoms. Hence, the electron pair is more attracted towards the chlorine atom than towards the hydrogen atom. In other words, the shared pair of electrons is more displaced towards the chlorine atom than towards hydrogen atom. As a result, the chlorine end of the molecule acquires a slight negative charge while the hydrogen end of the molecule acquires a slight positive charge. The bond thus formed between the two dissimilar atoms is called a polar covalent bond and the molecule is called dipole. Second one is dipole moment of a diatomic molecule. The extent of a polarity of a molecule is expressed in the terms of dipole moment, which is defined as follows. The dipole moment of a polar diatomic molecule is the product of the charge on each end of the molecule and the average distance between the center of the nuclei, that is the bond length. In general, for a polar diatomic molecule AB in which atom B is more electronegative than A, if plus Q is the charge on the end A and minus Q on the end B of the molecule, D is the average distance between the centers of the nuclei, then the dipole moment of the molecules AB is given by mu is equal to Q into D. Obviously, if the molecule is nonpolar, Q is equal to 0 and hence mu is equal to 0. Third is units of dipole moment. The charge present on the ends of the molecules is usually of the order of 10 raised to the power minus 10 ESU and the distance between the atoms is usually the order of 10 raised to the power minus 8 centimeter. Therefore, mu must be of the order of 10 raised to the power minus 10 into 10 raised to the power minus 8 is equal to 10 raised to the power minus 18. ESU centimeter. This value is called 1 dBi. Thus, 1 dBi is equal to 10 raised to the power minus 18 ESU centimeter. Fourth one is vector nature of the dipole moment. The dipole moment is a vector quantity, that is, it has both electronegativity, magnitude as well as direction. It is therefore represented by an arrow pointing from the positive end to the negative end of the molecule. Fifth one is dipole moment of a polyatomic molecule. In a polyatomic molecule containing more than two atoms, every two bonded atoms have their dipole moment. This is called the bond moment. The net dipole moment of the polyatomic molecule is the resultant of the different bond moments. Obviously, the resultant will depend upon the direction of the bonds. Thus, if a molecule AB2 contains two AB bonds at an angle of theta and mu AB is the value of each bond moment, then the dipole moment of the molecule will be mu is equal to 2 mu AB cos theta star by 2. There is a figure, that is figure 5.8. 5.8. Please carefully see. As mu is known from experiments, therefore knowing the value of theta, the method is usually used for the calculation of bond moments. Alternatively, knowing the value of mu and mu AB, the method can be used for the calculation of theta and hence for predicting the shape of molecules, as we discussed later. Thank you. Here the first part of this chapter is finished.